This is, let's say, 24. This is, let's say, 29, and here, let's say, this is 19. Okay. So one thing I just skipped right now, that is, okay. So here, the values of states are, here the value will be 1, here the value will be 3, and here the value will be 4. Why 1, 3, 4? Because already, while you are making node 18 as e node, you have assumed that queen 1 had a state 2, means queen 1 has been placed at 2, right? So for queen 2 we have available space at 1, 3 and 4 position. That's why 1, 3, 4 corresponding to these nodes 1, 3, 4. Okay, so this is the tree construction, very easy. Okay, and in this way we can further proceed to come up to the final tree construction. Okay, so while generating the node 3, one thing I forgot to mention, that is, this 3 node, okay, if I consider 1, after that 2, if I generate 3 node 3, that means I am considering a path x1 equal to 1, x2 equal to 2. Okay, that means this kind of a situation, q1 here and q2 here. Okay, which is not possible. Why not possible? Because this is violating the bounding function. What is the bounding function? The bounding function is no to. Oh, please, sorry, window is open. Right. So no to queen uh, can be placed in same diagonal. So this is my bounding function. So as per the bounding function, x1 equal to 1, x2 equal to 2 is not possible. That's why x1 equal to 1, x2 equal to 2 is not possible. So we want to delete immediately this node. Right. Okay. So this is the so far tree construction. Okay. Fine. So next, while generating node 19, node 24, node 29, corresponding to x2 equal to 1, 3 and 4, you see, if you place x1 equal to x1 q1 here and q2 equal to either 1, 3 or 4, right? So 1, 3 and 4. So as this is blocked, this is also blocked, right? These two positions are blocked. So this position corresponding to node 19, okay, node 19, and this position means this position, which is x2 equal to 3. So x2 equal to 3, x2 equal to 3 means this one. So both node 19 and 24 are violating the bounding function. That's why they are also deleted. Okay, so this is the so far tree construction as per the BFS branch and bound. Okay, next, so the 18 becomes dead node because all the children of node 18 were generated successfully. Okay, and so 18 becomes dead node. Next node, e node, have to be this one, 34. Okay, so 34 is the next e node, following the queue of live node. Okay, I forgot to mention here because 13 and we have removed 3 because 3 was not uh, 3 was 3 is not able to produce further depth of the tree. Okay, we can't find any solution further if I propagate including node 3. That's why it can't be a live node. it was immediately killed or deleted when it was violating the bounding function. Similarly, here 19 on 20, node 19 and node 24 were there, but as they were violating the bounding function, they were killed or deleted immediately after their generation. That's why 19 and 24 can't be live nodes. Only 21, 29 remained in the live node queue. Okay, so we place here 29. Okay, so after 13, 13, 18, 18, 29, 29. Right, it's correct. Right. Okay, next we move on to the next enode, which is node 34. So node 34 is my next enode, right? And after 34, so what we want to do, we want to explore 34 and produce all the children. Okay, so all the children, let's say children, let's say 35, node 35. Okay, and here 40 and here 45. Okay, which corresponds to, this is this corresponds to, okay, let me draw the edges. Okay, so this corresponds to, already 3 was used, so it should be 1 here, x2 equal to 1, here x2 equal to 2, here x equal to 3. Okay, x2 equal to 3. So now we are assuming that q1 is placed at q3, and you understand what is the BFS branch and bound technique, FIFO branch and bound technique. We are trying to iterate all the possible positions for queen 1, and then we are going into the depth of the chessboard, which was not in case of backtracking. Okay, so you remember the backtracking knowledge, backtracking technique. Okay, we first assumed one position for q1, and then we go for q2, then q3, then q4. So we are going along a depth of the tree. But here, first we are considering all the possible locations for q1 first. Then we will come up to q2. See, q3 and q4 are not yet considered so far, and this is the difference between FIFO branch and bound and the backtracking. Okay, okay. So if I place q1 here, so this will be blocked, this will be blocked. So available positions for q1, q2 is 1 and 3. Okay, so x2 equal to 1, x2, also this is blocked. So only x2 equal to 1 is possible. Okay, so x2 equal to 1, this is the x2 equal to 1. This is the x2 equal to 1, right? So this is only possible. Other nodes are not possible to be further expanded, right? That's why we want to delete this node, right? So this is the tree construction so far. Okay, similarly, if you want to explore 50, you can further propagate, no issue. Okay, okay, so I'm skipping that portion. Next, it is repetitive in nature, so you can understand. Next, let me write the live nodes. After 29, it will be 35, 35 generated. Yes, 35 generated. Next 50, 50 was there. Okay, so after 34, we want to 50 will be the next enode. We want to explore 50, and after, okay, so while 50 exploring 50, we will eventually see that the picture will be looking like 51 and 56. Okay, their corresponding states will be, here it is 1, here it is 2. Okay, the corresponding states, x2 equal to 1, x2 equal to 2. But the third child, 61, is not possible because x2 can't be equal to 3, because 3 is diagonal to 4. That's why. Okay, next, so 51, 56 were done. So 56 can be a possible live node. So 51, 56. Okay, then we want to, so 50 is done. Next live node, e node will be 8. So 8. Now we want to explore 8. Okay, so 8 can't be further expanded because all of its children can't lead us to a solution. Just you track, you just do it, you can understand. We want to move on to 29. Why 29? Because 29 can be expanded further. How? See, 29 may have two children. One is, let's say, 32. Another is, let's say, 30. 30 and 32, which corresponds to x3 equal to 2 and 4 were used, so it should be 1, it should be 3. Okay, so 2 4 1. So if I follow the path 2 4 1, can I reach a leaf node? 31, yes, I can reach a path which is in this case is possible 3. Okay, but if I follow 2 4 3, if I follow 2 4 3, then 2 4, so 2 4 1 3, sorry, 2 4 2 4 3, it was 3, right? So 2 4 3 is not possible, right? So it is not possible, so this node can't be generated, so this node can't be generated, right? So only this path we have. So we can traverse, we can find a path which can lead us, which can reach us, okay, to the leaf node. 31 is a leaf node. Okay, so this is a possible solution. So this is a possible solution. And what is the solution? We have found the solution is a 4 tuple 2 comma 4 comma 1 comma 3. So this is a 4 tuple. This is a possible solution. If I place 2 4 1 3, so then all the queens will be placed in such that they will not attack each other. Okay, so if you complete this overall tree based on BFS or FIFO branch and bound, the picture will be somewhat looking like this. Okay, so this is the picture, complete picture of the FIFO branch and bound based tree construction of the 4 queens problem. See, so this red colors, so 3 is red colored, so 3 was discarded, so this is discarded. Okay, then 8 was not expandable because 9 11 are not possible node. Okay, so they are red colored, so red colored are not possible, only the black colored is possible. So here we can find a black color, 18 29 30 31. Okay, so it's an answer node 2 4 1 3. We have found this solution, and another solution we can find. So from this observation we can understand only two solutions we can find to solve the 4 queens problem. There is no other path possible, okay, to traverse from root node to a leaf node. Okay, so see, 38 is black colored, 54 is black colored. So let's say this is level 1, level 2, level 3, level 4, level 5. So in level 3, 8, 13, 29, 35, 51, 56 are black colored. That's why they were sometime E nodes. So 1, 2, 18, 34, 50, okay, then 8, then 13, then 29, then 35, then 51, okay, then 56. So they were sometime, okay, E nodes because they were possible to be expanded, okay. But in next level, only we can see that only 30 is a black colored node, 38 is black colored, 54 is black colored. So only these three black colored nodes are possible to be further expanded. So they were the only three possible E nodes. Okay. So after 56, these are 30, 38 and 54. 30, 38 and 54. 30, 38 and 54. Okay. So while and immediately you write the live nodes. Live nodes means the nodes which are black colored, but their children are yet to be generated. Okay. So after 56, it should be 30, 38, 54. Okay. And also, okay, and also see 31 is black colored, 39 is black colored. But we see, though 54 was black colored, 55 is red colored because 54 was generated following the path x1 equal to 4, x2 equal to 1, x3 equal to 3. So 4, 1, 3. So is it possible a path 4, 1, 3? 4 means this is queen 1, 4, 1, 3. Okay, so 4, 1, 3, and see for queen 4, this is the only available position where the cursor is blinking, and this is violating, not satisfying the bounding function as it is diagonal to q3. So 4, 1, 3 is not a possible path which can lead us to a solution. That's why at the final stage, okay, 55 is not being generated. Okay, so only 31 and 39 are possibly generated. Okay, 31 and 39, 31 and 39. So 31 and 39, as they were generated, they will be live nodes, but we are not trying to expand them further, so they can't be E nodes. So see, up to this much, both Q of live nodes and new nodes are same. So the last nodes of live node Q are the leaf nodes. Okay, and the number of leaf nodes, okay, present in the live nodes will give us the number of possible solutions, which is 2. Okay? So the solutions are like so one solution what we have found, that is solution 1 is from the picture, what you can say, once this path. So this path is 2 4 1 3. Okay, so this path is 2 4 1, sorry, 2 4 1 and 3. So 2 4 1 3. Another is 3, then 1, then 4, then 2. So 3 1 4 2. So 3 1 3 comma 1 comma 4 comma 2. Okay, and the first solution was 2 4 1 3. Okay, so 2 4 1 3. Okay, and I just want to share with you that a semester question was asked, and also I have given you one question in the quiz, right, which was to be submitted by today 6 p.m. Okay, the semester question was find the two solutions of 4 queens problem. So I think this will be the best answer to write. Okay, so construct the tree using FIFO branch and brown technique, and then find two solutions. We have used backtracking to find solution of 4 queens. Okay, and we will also compare that backtracking today, and you will see using backtracking also we can find two solutions, but this is one other solution. Okay, fine. So that semester question was solved. Okay, fine. Next we move on to this is done. Next 4 queens problem using LIFO backtracking. Okay, so 4 queens problem using first in first out, LIFO or DFS based backtracking. Okay, so here we want to just see how many times. Oh, 110. Fine, fine. We can wrap up. No issue. Lot of time here. So Q of live nodes, Q of e nodes, and you can see here the difference between live nodes and e nodes better. Okay, fine. So here, let's see it. Again, we considered this problem, four queens chessboard problem. Okay, so first we are generating a node. Okay, let me save this. Save as image. Right. Okay. So let's say we have generated a node one. We start with node one, which is representing that no queens have been placed yet on the chessboard. Okay. So this is DFS backtracking. The topic is. Next, we want to move on to the next node here. Let's say 2. Here, right. So 2, because this is now DFS, and the path so far traversed is here x1 equal to 1. Okay, x1 equal to 1. Right. So next, let's see the quick queue. The queue of live nodes earlier was 1. Now it is 2. Okay. Okay, 2. We want to now next one has been see as this is backtracking, right? So backtracking, we were generating the node of 1, but not all the children of node 1 have been generated. Only one node has been generated, that is node 2, which corresponds to a path x1 equal to 1. So please keep in mind this is DFS. Okay, so then we are coming to the node 2, and node 2 becomes the next e node. So before completion of generation of all the children of node 1, we are now have started exploring node 2. So this is DFS backtracking, but not DFS branch and bound. So here is the difference. What is the difference? Will be generated first before making next live node as next e node. So though one was a live node, but we have not generated all the children for one. We have moved on to the next node, next live node as e node. So this is not branch and bound. This is backtracking. So this is the difference between backtracking, DFS backtracking, and DFS branch and bound. Okay, so please understand very clearly the difference. I hope this is clear. So next 2. So at this moment we want to further explore node 2. So the possible children are this one, let's say 3, this is 8, and this is 13. Okay. Okay, so this corresponds to x2 equal to 4, this is x2 equal to 3, this is x2 equal to 2, right? So these are the expansions of node 2, but out of which this node 3 is violating the bounding function, and hence it is deleted. Okay, so only node 8 and 3 are satisfying uh, node 8, the bounding function. Okay, fine. So Next what? At this moment it is 8. Live nodes 18, 8 and 13. Okay, and Q node, next Q node will be this 8. 8 will be the next E node, because 3 was deleted. Node 3 was deleted. So node 8 will be next E node. Okay, so we want to now explore node 8. Okay, so let's explore it. So if we try to explore this, we will come up to this one node, let's say 9. This is node 11. Okay, so this is these are the two possible children, and corresponding to here this is I think 1 3, this is 2, and this is 4, right? So you see, these are not possible nodes, because 1 2 1 3 2 is not possible, violating the bounding function. 1 3 2, so 2 and 3, these are diagonal. Okay, so these are not possible, and that's why this is discarded or deleted. This node is deleted. Similarly, 1 3 and 4 is also not possible. 1 3 and 4, so this is 1, this is 4 and 3, so 3 4 are diagonal, so hence these are also not possible. So 8 can't be possibly expanded. Next, E node becomes 13. Okay, so next E node becomes 13. So similarly we can expand, similarly we can understand, right, we can expand 13 further. Okay, so this is, let's say, node 14, and okay, so node 14 corresponding to x3 equal to 2, x3 equal to 2. Okay, so 14 becomes the live node. Next next node, E node will be 14. Next E node will be 14. Okay, so 1 4 2 already used. 1 4 2 already used. Available position is 3. So 3 is diagonal to 2. So 3 can't be possible. So as 3 can't be possible, so this node can't have any child. Okay, so if we draw that child, so let's say this is a 15. So this is not possible. So this is not possible. Okay, so okay, I forgot to mention what is the backtracking. Backtracking means, as this node is not possible, so simply it will be deleted and will come up to this point, then it will come back to this node, then will come back to this node, then will come back to this node, so that this node is further expanded. So this is the meaning of backtracking. Okay, fine. So if I see the overall picture, now you can understand what is the picture. Okay, so now the overall picture is looking like this. If you proceed like way, so you can have this picture. So you can see the red colored nodes. 3 is red colored, 9 11 15 16 were red colored. Okay, so and where the backtracking was happening, that was mentioned, B signifying that this node is deleted or killed, as this is violating the bounding function, and hence backtracking occurs. So from all the nodes from where the backtracking was occurring, have been mentioned as capital B. Okay, so let's come to, so this subtree can't lead us to a possible solution. So this tree is simply discarded. Next we come up to this node, node number 1, and first 18 will be generated, not 34 will be generated, and 50 will not be generated. So next generated node is 18. So 18 becomes the next live node. After 14 it will be the next uh, live node. Okay, and it will be eventually the next inode also. Okay, because it will be the next uh, expanded, explode. Okay, so after while exploring 18, we can find that 1924 children are not possible children, so they were deleted immediately. So first child 19 will be generated and it is violating the bounding function, so immediately it is deleted, and 19 can't be the part of, you know, the live node. Okay, so next similarly it backtracks to node 18 and generates the next possible child, which is 24. As 24 is violating the bounding function, it is deleted and is never part of the live node queue, and then it backtracks to node 18. Next, from node 18, the third possible child is generated, 29, which is not violating any bounding function. So 29 becomes added to the queue. Okay. Also, this becomes the next inode. So we are now exploring 29. So two children are possible at this level. Okay. So two more children, 30 and 32. So out of 30 and 32, right. So out of 30 and 32, 32 is violating bounding function. Okay, sorry. So in backtracking, you know, and DFS backtracking, when 29 was inode, only first child 30 will be generated, not 32. 30 is being only generated, not 32. So as 30 is generated, 30 becomes the next live node, and 30 also becomes the next inode. Okay, so you can see the live nodes and e nodes queue are going parallel to each other, while these were not parallel in case of BFS branch and bound. Okay, so next what is there? Okay, so in the picture, so 30 explode, and from 30, after exploration we can generate a possible node 31, and which is not violating any bounding function. Okay, so next live node is 31 here, and this is a live node, a leaf node, and stop here. So as this is a leaf node, we have successfully reached one of the leaf node, and the possible solution in that case is the path is sorry, this picture, this is 2, this is 4 1 3, 2 4 1 3, same solution, 2 4 1 3. So this is the solution. So this is DFS backtracking, and after understanding these two pictures, this is the picture of branch and bound. Okay, just ignore the red colors, you will have the complete tree construction. Okay, tree picture, which is the back branch and bound, and this picture is DFS backtracking. And one thing I want to mention that here for your understanding, this is marked as 1, then this is 2, then 3, then 4, then 5. What are these things? The order of generation of the nodes, means the order of the live nodes. See, the live nodes are in earlier case live nodes are 1 to 18 34 50, 1 to 18 34 50. So 1 to 18 34 50. So the live nodes are given some order or index. So 1 2 3 4 5, these are green colored, then 6 7 8 9 10 11 12 13 14 and so on. So ultimately you see the last index, green colored index, is 32, means this one, 55. Okay, so but in case of this picture, similar indexing we are doing in case of backtracking. So this is the green colored number 1, next generated node is 2, next is 3. Unlike branch and bound, it was supposed to be green color 3. Okay, but here it is green color 3. So this is the difference. So 3, 4, then 5, then 6, 7, 8, and so on. And you see the last index while finding the first solution is 16. And in case of backtracking, branch and bound, in case of branch and bound, this was the node where we have found the first solution, and the corresponding index is 30. So in what we have observed, that is, to find the first solution, okay, backtracking uh, okay reaches only x 16, I hope 16, right, 16, and it is 30. Okay, so 16, while branch and reaches an index of 30. That means minimum 16 nodes have to be generated, and here minimum 30 nodes have to be generated to find the first solution. That means backtracking is faster than branch and bound. Okay, so hence backtracking is faster than branch and bound technique in this problem, 4 queens problem solution. ठीक है? So this is the thing. Hence backtracking is faster than this is, and also in terms of, and also space efficient, because we are requiring a storage for queue of live nodes and a queue of e nodes. See, this is the length of the queue, and here this is the length of a queue. Here this is, so which is larger than this one. Okay, so this is space efficient, also time efficient, backtracking, then branch and bound. Okay, so this is the discussion. What is the branch and bound? Just yeah, okay, and I can give you one home task. So apply. You got to know now that what is FIFO, branch and bound, and then what is LIFO. Okay, so now apply LIFO, branch and bound. Okay, and construct the tree, which is the state space tree, which is the state space tree for 4 queens problem. Hence find solutions. Not only one solution, hence find all possible solutions. All possible solutions. So this is a very good problem. So please try to answer this one. Okay, it will be a part of quiz also. Okay. Okay, so 129. So can we extend it to another 3-4 minutes? People allow me? What do you say? Just 5 minutes more, because we want to continue, we want to explore network flow in the next class. So just it will be an introduction. Okay, so it will be an introduction, right? So here what we are, so flow network, right? So what is a network flow or flow network? Okay, so that is a network is a directed graph. Okay, the network is a directed graph. Okay, directed graph where each edge will have a capacity. Okay, we normally denote capacity of an edge UV by this one. Edge is denoted by U comma V, where U V are vertices of that graph G, of any directed graph G. Okay, so CUV will have a capacity greater than equal to 0, full stop. So there is a source vertex S and a sink vertex. These are terminologies T. Okay, so network is fine. So next we define the network flow like this. Okay, a flow F in a network means a directed graph G is a real valued function. Real valued function means something like this. Uh, F colon R sorry V uh, cross V to R, right? So this is the thing. Okay. So this is the thing. F equal to F is a flow, okay, which is a vertex. B is the vertex set of the graph G, and R is the set of any real numbers. So F is nothing but a real valued function. Okay, fine. Right. Okay. So next, what we do, having this, we want to define a flow of network G such that number one is f of u comma v uh, must be less than or equal to the capacity c u comma. This is known as capacity rule. So whatever be the capacity, the flow can't exceed that capacity. Okay. Next, f of u comma v is equals to minus of f v comma u. So I will shortly come to one illustration. This is known as skew property, skew symmetric property, skew symmetric property. The third rule is if, I mean, for every vertex V belongs to V in capital V belongs to V, we must satisfy this thing that sum of f u comma v, okay, so is equals to f sum of f w comma v, sorry, this is v comma w, intermediate vertex is v. Okay, so this is for every u in capital V, and this is for every w in vertex set v. Okay, so this is the picture. So f of uv, so this f of uv, okay, shortly coming to this one, let's draw a picture. Okay, let's draw a picture. So let's say we have a vertex like this. Okay, so this is a directed graph. So we are putting the directions. Here it is sorry, directed like this, and here it is directed here. So this is directed here, directed. Right. So these are the directions. Okay, and what we want to say that right here, that is let's say this is 1 by 3, and let's say this is 1 by 1. Let's say this is 1 by 3. This is 1 by 3, and this is 0 uh, by 2. Okay, so then this is, let's say, 1 by 1, and this is 1 upon 3. Okay, and this is 0 by 2, and this is left, so this is also, let's say, 0 by 2. Okay, so this is a network. Okay, and let's say this is my S, and this is, T, source, and this is sink. Okay, so this FUV means, let's say, consider this vertex. This vertex is, let's say, B. Okay, so for this vertex B, okay, for this vertex B, F, incoming flow, F equal to, so for vertex B, two incoming edges we have. One is this vertex, which is assigned a level 1 by 1, another edge is 0 by 2. Okay, this edge, these are the incoming edges. Okay, and I want to forget anything. What is this thing? The F by C. So this is the flow of any edge. All the edges are labeled like this, some value by some value. The first value is representing the flow, and the next value, right side value, is the capacity. And all the edges are defined edges, means they are satisfying the first rule, capacity rule. The flows are always less than or equal to the capacity. Okay, and okay, and then this is not required, skew symmetry for this graph. And we are now trying to understand the third rule, which is for any vertex B, the incoming edges are these are, of which the flows are here 1 and here 0. So here the incoming flow is 1 plus 0 equal to 1, incoming flow. And what is the outgoing flow? Outgoing flow, which is outgoing edges, is this one, which is labeled as 1 by 3. No other outgoing edge is present for vertex B. And for the outgoing edge, we have the flow is only 1. So this left hand summation denotes the incoming flow for any vertex, and the right hand summation is denoting the outgoing flow, this one. And you see the incoming flow summation 1 and outgoing flow summation 1. These have to be equal for every vertex present in the graph. Otherwise, that graph will not be called network flow or flow network. That will violate the last. This is called, actually, this called is flow conversion rule. This is known as flow conversion. Okay, flow conversion rule. So now what is our problem? The main problem why we are trying to study this topic, because our objective is, the goal is to find maximum flow of a network, maximum flow from S to T. S is the source vertex, T is the sink vertex. So we have to find a maximum flow from source S vertex to a sink vertex T in a network, in a flow network, or network flow, whatever, or network flow. So that means this problem is nothing but an optimization problem. Okay, so we have already understood, we have covered all the optimization problem algorithms like greedy, branch and bound, backtracking, dynamic, brute force, etc. etc. Okay, so anyone or among these optimization algorithm can be applied to solve this optimization problem. Okay, so with this I want to conclude. This is the introduction to the next topic, which is based on network flow and Ford Fulkerson algorithm and max flow mean cut theorem. Okay, so with this I want to conclude and I will share everything. So if you have any question, please ask me. So far, any question up to this? No?